In this tutorial, I'd like to talk about whether radiometric dating works on all rock types. If you've watched my previous tutorials, you found out that the answer to that question is no, and that radiometric dating works best on the igneous rocks. There's several different reasons for that. One simple reason is that when we date a mineral that's in an igneous rock, that gives us the age of the rock as a whole. Why is that? From our previous tutorials, we learned that when a mineral crystallizes from a magma, certain minerals anyway, will trap in radioactive isotope atoms, or what I call parent atoms. And once they're trapped in the solid mineral crystal, they can't get out. And then the radioactive parents will decay to form stable daughter isotopes. So as time goes on, we have more and more stable daughter isotopes trapped in our mineral and fewer radioactive parent isotopes. Because all igneous rocks form from the cooling and crystallization of magma, and that happens geologically in an instant, all of the minerals in a given igneous rock are the same age, and they're the same age as the rock itself. Now, another reason why igneous rocks are so good for doing the radiometric dating is that the magmas form down in the Earth's interior where there's lots of radioactive isotopes to be trapped in the minerals once the magma cools and crystallizes. That doesn't mean that all igneous rocks can be dated radiometrically. We learned in a previous tutorial that if an igneous rock is heated after it forms, maybe like due to metamorphism, that heating will cause the bonds to break within our mineral crystals, and some of the radioactive parent or stable daughter isotopes could leak out of or into the mineral. So our parent-daughter isotope ratios that we measure are thrown way off, and they're not reflective of the age of the mineral or rock itself. I also mentioned in a previous video that there's a form of radiometric dating called isochron dating, and when you do the analysis for isochron dating, it becomes pretty clear if your rock is one of those where there was a heating event that threw off the parent-daughter isotope ratios, and in that case, you would not be able to use that rock for radiometric dating. Now, what about the metamorphic rocks? Speaking of heating, can metamorphic rocks be dated radiometrically? And the answer is, well, maybe. Now, most metamorphism is accompanied by heating events, and we know that heating events cause problems with radiometric age dates. However, if the metamorphic event resulted in extensive heating to the point that minerals in the metamorphic rock experienced wholesale breaking of bonds and release of parent and daughter isotopes, then those parent isotopes, or in some cases it's parent and daughter isotopes, can be trapped in a mineral that's forming during the metamorphic event. And then for those minerals, if the geologist comes around many millions of years later and analyzes those minerals radiometrically, they will give the age of the heating event or the metamorphic event. Unfortunately, some metamorphic rocks don't get heated up that much. Other metamorphic rocks experience multiple episodes of heating, so it can be difficult to pinpoint a particular age for some metamorphic rocks. But next to the igneous rocks, some of our better candidates for radiometric dating do come from the at least intermediate to high-grade metamorphic rocks. Well, that leaves us with the sedimentary rocks, and the sad story here is that very few sedimentary rocks can be dated radiometrically, and that's why we still use relative dating techniques a lot to understand something about the age of sedimentary rocks. Now, what's the deal or problem with the sedimentary rocks? Well, if we think about the clastic sedimentary rocks, or you might have learned them with the name detrital sedimentary rocks, but they're the ones where the minerals within the rock were derived from the uplift and subsequent weathering of often many different original rocks. And then, there's transportation of the weathered debris, deposition, lithification of the sediments, and when we pluck a mineral out of a clastic sedimentary rock, that's telling us when the original rock from which that sediment was derived formed. It's not telling us the age of the sedimentary rock itself. Sedimentary rocks, with those, the age we're looking for is we want to know when were those sediments being deposited to form the sedimentary rock. And that information does not come from radiometric age dates of minerals in clastic sedimentary rocks, most commonly. So let's think about the chemical sedimentary rocks or biochemical sedimentary rocks. What about those? The problem there is the minerals that form from either like precipitation of water or when an organism takes ions out of seawater or whatever water to make their hard parts. The problem is that in those environments, there's not a lot of radioactive isotopes, and as a result, there aren't a lot of original parent radioisotopes that get incorporated into the minerals in our chemical sedimentary rocks, generally speaking. There are exceptions to that. So what do? We have to use relative dating techniques to learn something about the ages of our sedimentary rocks, and there is one exception to this where we can use radiocarbon dating or carbon-14 dating. But that's only applicable or useful for very young sedimentary materials. Now, the carbon-14 dating works differently from what we described in previous tutorials about radiometric dating for our igneous rocks. Carbon-14 is actually incorporated into plant material. During photosynthesis, our plants take in carbon dioxide from the atmosphere, and a small percentage of the carbon in that carbon dioxide is the radioactive carbon-14. Now, when the plant dies, of course, it doesn't do photosynthesis anymore, so it stops taking in the carbon-14. The carbon-14 that's in the plant material decays to stable nitrogen-14. So if our plant remains are buried in something like an ancient soil, or if we have wood or even charcoal and that's buried in sediment, that's going to be our source material for the radiocarbon dating. Now, problem with carbon-14 dating is carbon-14 has a very short half-life. It's only about 5,700 year half-life. And as a rule of thumb, after about 10 half-lives go by, there's too little parent isotope left in the material for even our sophisticated solid-state mass spectrometers to actually measure. So the carbon-14 dating is really not useful on things more than about 60,000 years old or so. That limits the usefulness to very young sedimentary materials. Well, I hope this has helped you understand some of the limitations of radiometric dating. There are an awful lot of igneous rocks and good metamorphic rocks in the world to use for getting absolute age dates using radiometric dating.